So in the previous video, we derived this equation right here, which is pretty useful because what it does is it essentially allows us to relate something that we know about the equilibrium position of a reaction with something having to do with the amount of Gibbs free energy. So to get a sense of what this equation means, we're going to evaluate it under two different situations. All right. First, we're going to consider a reaction where the KEQ is 100. All right. So remember, if the KEQ is 100, let's, for example, take this reaction right here. This would be how you could write the equilibrium expression. And essentially, what this KEQ would mean is that at equilibrium, there would be a 100-to-1 ratio between B to A. So realizing that, we could certainly say that this reaction favors products. All right. So let's think about what this would mean. All right. So earlier we showed these reaction graphs. All right, where you had free energy over here, and we had this would be all A, and this would be all this would be all reactants. This would be all products over here. And if something favors products, that minimum energy would be more towards the right. All right. So So remember, this is going to be where the reaction is at equilibrium. All right, and the concentrations at equilibrium are not the same as what the not necessarily the same as what the concentrations would be at standard conditions. All right, standard conditions are where the concentration of the reactants and products are all at 1 molar. All right, so if in a situation where you've got where products are favored at equilibrium, the equilibrium position would be about right here. All right, but the standard conditions would be more like right towards the center. All right, so if you just say this right here, if both of these are 1 molar, all right, then that's halfway between 100% A and 100% B. All right, so that would be right there in the middle. All right, so let's just look at this and think about what we would predict based on Le Chatelier's principle. All right, so if we know that this is where the equilibrium wants to be, but this is where we actually are, then what would be the tendency? All right, well, it's going to want to move towards that equilibrium. All right, so, and we learned before that whenever a reaction, the driving force is for it to go to the right as written, that corresponds to a negative delta G. All right, so based on Le Chatelier's principle, our intuition is that in this situation here, all right, if you had something where things were at standard conditions, at that position, your delta G would be negative because it wants to go towards the right. All right, so let's do it mathematically. All right, so if we took this expression right here and we plugged in 100, all right, for your ln. All right, well, one thing about an ln of a number that's greater than 1 is that the natural log of that is going to be positive. All right, so what we could do is I'm not going to plug in actual numbers here. I'm just going to evaluate what the signs of these things are so that we can see what it means. All right, so we're going to have an expression here where you've got your negative. All right, you're going to multiply that by R, which is a positive number. T, that's in Kelvin, so all of those are positive. All right, and your ln, your natural log of this large number, is going to be positive. So all of these things multiplied by each other are going to give a negative value. All right, and that's consistent with what we would have predicted earlier. All right, so what this equation is actually going to do is instead of just saying, hey, it's negative, it's going to say exactly how much delta G, or Gibbs free energy, what are we having getting from here to here. All right, so it's going to quantify that. All right, so let's just think about the opposite condition, all right, where you had a KEQ which was much less than 1, all right? So if it was like 0.01, essentially what that would mean is that there's a 1 to 100 ratio between the products and the reactants. So this is going to be something that is considered to favor reactants, all right? So that would mean that your equilibrium position would be right here, and it's now on the other side of where those standard conditions are, because standard conditions is when there's 1 molar of reactants and products. All right, so in this situation, what would be the driving force if you were at this position right here? Well, the driving force would, just using Le Chatelier's principle, would be things should want to go to the left. All right, things want to make some more of the reactants to get to that equilibrium. All right, and we know that when things want to go towards the left, the way the reaction is written, that would correspond to a positive delta G. All right, so going through just the same mental exercise that we did before. All right, we would have a natural log of 0.01, and since that is less than 1, all right, so whenever you take the natural log of a number that's less than 1, it's going to be a negative value. All right, so a negative times a positive times a positive times a negative is going to overall give us a positive number. All right, and this is consistent with what we would have predicted. All right, so why is it that this delta G, first of all, note that if we know the KEQ, all right, and we can determine what equilibrium constants are, it gives us a way to calculate this special value, all right, which is the Gibbs free energy at standard state. All right, so why is it useful? Well, ask yourself this. If I were to show you a reaction and say, what's the just plain old Gibbs free energy, all right, of this reaction, it's impossible to answer that question, because you'd have to say, well, at what point in this reaction? All right, are we talking about the Gibbs free energy when it's 100% C? Or are we talking about the Gibbs free energy when it's 100% D? Are we talking about it when it's mostly D? All right, so if you ask yourself, how many different combinations of concentrations could we have for this particular reaction? All right, and the answer is an infinite amount. All right, so since there's an infinite amount of different concentrations here, there would be technically an infinite number of delta G's for this particular reaction, because it all depends on where we are along the spectrum. All right, so the value of delta G is that it allows us to basically compare apples to apples. All right, if I've got this reaction right here, which is different from this reaction right here, well, how could I, get a sense for, changes in free energy? Well, the way we do that is we say, okay, we're going to measure all these delta G's under one special set of conditions. All right, and that's going to be that standard state where everything starts at concentrations of 1, and because we're only doing it under one set of conditions, we can have one common value that can be determined for a specific reaction. All right, so for any given reaction, if it was an actual chemical reaction, you can look up in references and find what the standard state delta G would be. All right, and one reason that that's useful is if we go back to our the equation that we were using in the previous video, if we know this right here, we can look that up in a value. All right, sorry, we can look that up in a reference table. All right, we could, and if we knew what the current concentrations were, all right, we could plug that in here. We could use both of those information bits of information together to calculate what the actual delta G is at that position. All right, and that's a pretty useful thing to be able to do.